Hi, welcome to Turkish Engineering. In this lecture, we are going to study Newton's laws of motion. So, as you see here, we moved from part 1 of the chapter 4. So we finished it, and we have just 5 more parts, and we will finish all of them, or let's say just 4 of them in this video, and the last part, which is free body diagrams, will be in the next video. So I will just actually, before the high school and in the high school in the 9th grade and in the 11th grade and in the 12th grade, we are just repeating a lot what are Newton's laws of motion. So actually you heard about these laws, but I will just repeat them and make some brief introductions. Actually the understanding of laws of motion is not too complicated, but the applications of these laws in some problems, in inclined planes, in just some different cases, will be sometimes difficult. So chapter 4 will be easy. Then when we move to chapter 5, which is applications of Newton's laws, we will see some different problems and difficult problems, but we will handle them. So let's talk about the laws of motion. So the first law is just some words which are explaining the inertia. So it is the law of inertia. Any object, if it's at rest, will remain at rest, and if it's moving with a constant velocity or moving with a uniform motion, it will continue and it will remain at this uniform motion. Until what? Actually, they will be at the same state until what? Because of they have inertia, which is the property for any object in the space or in the universe. So you will have a property which is called inertia. So you will have tendency to not change your state. So if you are moving, you will keep moving. If you are at rest, you will keep at rest. You will remain at rest until what? Actually, you will need a net force or unbalanced force. So if you have an unbalanced force, that means you can accelerate. So your velocity will change. If you are moving at the same direction, you can move your direction with a force. If you are at rest, if somebody pushes you or any force just pull you up or just push you, so you may accelerate when these forces are unbalanced. So you will accelerate. But if you have some forces which are acting on you. So for example, I'm now sitting on the chair and I have gravity which is pulling me down, but because of the normal force which is coming from the ground acting on the chair, and the chair is acting on me, so I am not moving and I'm at rest. Why? Because of the first law. So because of the inertia, if there is no net force, I will not move. And some just comments from physics students, I got them from some YouTube videos. They commented by this way to just simplifying the first law. A student in bed will remain in bed until acted upon by a large enough panic. So as you have some enough panic in the exam week, so you will wake up and you will study. So it is coming from your inertia. A jobless man will remain jobless unless offered for a good job with a good salary. So force will not be enough, as same as bad job. If somebody is offering you for a bad job and with a bad salary, you will say, oh, no, I have inertia, I have tendency to do nothing, so I will just sleep and I will not work. But if somebody comes to you and just offering a good job with a good salary, you can say that, yes, you overcome to my inertia, so you won. You won the game because you have just an unbalanced force which is winning against the inertia. So when you come with a good salary and good job, you will just win against the inertia of the jobless man. So as you see, this is the picture which is taken after pulling this table, which has these objects on it fastly. So quickly I will remove this table. What will you see? Actually, in this moment you will see that they are at the same position. Why? They didn't go in the same direction of the table. Because of their inertia and there is no force applying on them in the x-axis, actually the table is pulled in this direction. What about these? There is no forces acting on these objects, so they will remain at the same position in the x. But after some milliseconds, you will see that they are pulling down by gravitational force. Why they didn't move when they are on the table, and now they will accelerate down? Because when they are on the table, there are two forces, which is one of them downward and the other one upward. So they are balancing each other. The first force is weight of the object, which is pulling down, and the second force is normal force, which is coming from the table. So table's surface will apply a force to the object, so that will make the object stable in the y-axis. But when you just cut the contact, of the surface by the objects, you will see that they will accelerate down if they are in the Earth atmosphere. But if they are in the space, you will see that when you take the table, actually they will not move. They will not move neither in x or y directions, because there is no force acting on them, nor inertia, nor in y-axis or in x-axis, because there is no gravity force which is pulling down, and there is no pushing or pulling force in the x-axis. So you will see that they will just remain at the same location because of law of inertia. So this one. Actually, when you have two objects, one of them has less mass, and the other one has more mass, what do you think? To move the biggest or the massive object will be easier, or to move this object will be easier? Actually, more mass will give you more inertia. That means if the objects which have more mass will have more inertia, so that will be difficult to change their state. If any object, actually just assume, think about the truck. Truck has more mass, right? So if truck is moving, it will be just so difficult to stop the truck, right? Because of its inertia. So if it's moving, it will keep moving at the same direction, at the same velocity, until a net force effect on it. So what about if the initial state of the truck was at rest, so it will be very difficult to move and give the first push for this truck to move. So that means more inertia will come from more mass. So this is the first law. What about the second? Actually, let's talk about the second law. Okay. The second law will be the mathematical relation between mass, acceleration, and force. Actually, in this section, we are trying to see what are the factors affecting the acceleration. So we will make a lot of experiments. We will change the temperature of the object and see if the high temperature one is moving with high acceleration. Or we will change the volume. So we will see, after some experiments, we will see that temperature will not affect the acceleration, and actually the volume will not affect. Some different properties will not affect the acceleration. Only two will affect. So the mass and the force. One of them is inversely proportional, and the second one is directly proportional. So what do you think? More force will give you more acceleration or less? Actually, will give you more acceleration. So force is directly proportional to acceleration. What about the mass? If you have more mass, that you will get more acceleration or less acceleration? Actually, if you have more mass, you will get less acceleration. So that means they are inversely proportional to each other. So we will have two cases here. The first case, you will keep mass as the same. So you will keep mass as the same, but you will double the force. When you double the force, the acceleration will double. So that means they are directly proportional to each other in the first order. Because when you double the force, you are getting the same amount of acceleration change. It's doubling. So that means they are directly proportional and at the same rate. That means you can put this relation. Acceleration will be directly proportional to the f itself, not the f squared and not the f of 2, not the f of just to the 3. It's just f, because they are directly proportional in the same rate. So you can put a equals to f, but if you don't have any actually factor, the formula will be just a equals to f. More f will give you more a. But you have second factor, which is mass. So you must come with a formula which will combine two factors and our base, which is the acceleration. We are searching for acceleration factors. So we will make a second case between A and C. Between A and C, as you see, I doubled the mass, but the force is actually equal to each other. So as you see, the mass is doubled. So here I have two mass, but the force is same. So what will you see? Actually, the acceleration will be half. So when you double the mass, you will get half of the acceleration. That means they are inversely proportional to each other in the first order, because you are doubling and dividing by 2 the other one. You are doubling, multiplying 1 by 2. The other one will be divided by 2. So that means they are actually in the first order. Actually, what I mean by first order, that means to the 1, not to the 2 or to the 3. When I double the mass, if I get quarter of the acceleration, that means they are not proportional to each other in the first order, actually in the second order, because one is multiplying by 2 and the other one is dividing by 4. So 2 times 4 is square of 2, right? So in the second order, I have relationships in the second order. But if I double this one, so if I multiply this one by 2, I will divide the other one by 2, so they are equal to each other. That means they are at the same rate, but reversely proportional or inversely proportional to each other. So I will get this one. As you see here, a equals to f, and here a equals to 1 over m. When you combine these two, you will get a equals to f divided by m. Or if you are searching for the f or for the force, you will get f equals to ma. Actually, this is the second law. F equals to ma. But you must say, if you have one force, you can say f. But if you have different forces acting on the body, so you will say the f divided by m, or you will put just this one. Summation of all forces, which is the net force, will be equal to m times a. So you must put this one, the summation of all forces. So this is the second law. If we are now moved to the part 4 for the for chapter 4 part 2, we studied the first law. First law. And the third part was the second law. And the fourth part will be just mass and weight. So we are now in this part. Will be easy, just weight equals to mg. So when you need to calculate the weight, so you will multiply mass by g. And actually, maybe you know this rule. And actually, it is coming from F equals to ma, the second law. So you have weight here. And this is free falling down. So the summation of forces will be just W. And that must be equal to ma. And actually, it is accelerating down by which acceleration? The gravitational acceleration. So instead of ma, you will put mg. So this is just chapter 4.4. Just weight equals to mg, which is coming from the same idea. Any force equals to ma, so the weight will be equal to mg. Okay. Now we will study the third law, the third law of motion. This is just a simple idea. When you apply any force, you will get for any object. This object will apply a reaction force. So for any action force, there will be a reaction which is equal in magnitude and opposite in direction. So this is the third law. Every action has an equal and opposite reaction. Okay, so this is the third law. Actually, When you are swimming, you are using the third law. Without knowing third law, from your observation and from your father's observation, actually you will be studied how to swim. You will be taught it from your father or from your mother. They will say that please just make this motion, right? So they will say that please push the water back. Push the water back. That will make you move upward, forward. So how they know this one? Actually, it is coming from our simple observations. Actually, your father or mother, maybe they didn't study third law, but they will say we will make this just action. So you will get a reaction from the water which pulls you, which will push you up forward. So actually, a bird which doesn't know the third law will apply third law, and it's coming from its nature. So the bird will push the air down. So we'll push the air down, and the air will has an opposite reaction force, which is pushing upward. So when the bird is pushing down the air, so this force will push up, the air will oppositely push the bird up, so that will make the bird accelerating up and moving up. And when we are swimming, the pushing force which is coming from us is backward, but the motion is the motion is forward, and the pushing from the water onto you will be forward. This is coming from the third law. As you see, a frog which is swimming will push the water backward, and the water will push on the frog in the forward direction. And this is a bird which is flying, push downward, so air will push the bird upward. Okay. So this is one of the comments of the students. Actually, they know how to come with good sentences. So he did his own experiment by hitting his dad, and he reacted. So any action will has an opposite and equal reaction. Actually, I think the reaction force of his dad was bigger. So now we finished all laws of motion, the first law and second law and the third law. You can watch some videos for the laws of motion to see some real life examples. Because our time is limited, I will not show some real life examples in this video. Actually, I have just digital sources here. I cannot show now some real life examples, but I gave some examples, just some words, just a frog, a bird, and when you're swimming, and when you're pushing, actually when your weight is pushing down, so the ground will push you up. But when we solve some examples, you will take some real life examples and how we apply the Newton's laws on some real life questions. Let's finish the last part, which is 4.6, last part. And then we will just have only one additional video, and we will solve a lot of problems, or maybe I will divide it into two videos, so you will see a lot of problems for chapter 4. In chapter 4.6, the last part for the chapter 4, we will talk about free body diagrams. Free body diagrams. Actually, this is a simple idea for representing all forces onto one point. So in this example, I have a card which is pulled with the second card, and I have a rope here. So let's say that we have a guy here which is pulling this rope, okay, which is pulling this rope in this direction. Okay, so the card B and the card A will accelerate if this force is enough to overcome about the friction. And actually it is a frictionless surface. So if we have a frictionless surface, actually a small amount of force will be enough to accelerate any object. And you will see that in the space. In this just real case, in the earth, you will not see. When you, for example, I have a chair, I have a table in front of me, which my laptop and my old stuff is above of it. So I will try to push a little bit. Actually, it's not moving, because I'm slightly applying just small force. But if I apply the same force in the space, because there is no friction, and there is no resistance in the air or in the surface, you will see that it will accelerate easily. Even a little force will accelerate, will make this object accelerate. So it is like just in a space. So when you push with a small force, it must be accelerate, right? So how can we put free body diagrams? Here I can make 4 free body diagrams because I have 4 objects. Card A is the first object, rope 1 is the second object, card B is the third object, and rope 2 is the fourth object, and which I draw here is the 5th object. So I can make 5 free body diagrams. Okay, so I will take this down and I will put free body diagrams for all of my objects. So let's start by card A. I can put just a point. You must, and you don't have to put just the same shape, then put the forces. No, let's say that this is the card A, just a particle, okay, and just show the forces. I have the weight which is pulling down, and as you know from the third law, I must have a reaction force which is coming from the ground, and it is normal force. And because of this object is frictionless, I will not put here friction force because this is frictionless. So I will not put friction force. But from the rope 1, I have tension force. So it will has only 3 forces. What about the second one, rope 1? Rope 1 will have tension here and tension here. And actually, let's say this is massless rope. The mass will be too small so we can neglect it. So the rope which is actually will have a weight which is pulling down, I can neglect this weight because the rope will be treated as massless, so it will be very small in mass, so I will neglect it. What about this third object, card A? We'll have the same as this one, but we have weight and normal force, and rope 2 which is tension 2, and these are tension 1. So but here I will have tension 1. And actually the tension 2 will be bigger because it's accelerating this way. So tension 2 must be bigger than this one to make it accelerate in the positive direction. Rope 2 will be as same as just rope 1, but tension 2 and tension 2. And this guy just put another point here. Weight will has weight, and just here we have normal force, and actually this guy will be pulled from the rope in this direction, right? Tension. But because actually it will push the ground, this guy will push the ground in an inclined way to make this rope accelerate in this way. So actually this guy can move in the forward direction. Actually to move this rope and these all objects, the guy must accelerate in the forward direction, right? So the force which is in the right direction, in the positive x direction, is coming from the third law. So this guy will push the ground by his muscles, so can accelerate in the forward direction. So I will have a normal force which is in this direction, and you can say the F, which is coming from his muscles, so trying to push the backward for the ground and try to move and run in this direction. So this is the free body diagrams, and we will solve some different problems and see the application of free body diagrams and second law and third law, and we will finish chapter 4. Then we will move to chapter 5, which will be just basic applications for chapter 4, but we will take some more additional informations about the forces. So see you in the next video for solving the problems of chapter 4.